Good morning, good afternoon, good evening, ladies and gentlemen. A very warm welcome to you all to the first ever GoTo Data Science Conference. My name is Gaurav, and I lead data science teams for recommendation, personalization, and customer service at Tokopedia. And I have the pleasure of being your host today. Today and tomorrow, you'll hear from among the brightest data scientists at the GoTo Group. They'll share about how they solve some of the most challenging problems with machine learning. You'll essentially be witnessing the evolution of data science at Gojek, Tokopedia, and GoTo Financial. And that's just the cake, by the way. To add the icing, my friends, we have invited global experts for the plenary talks and panel discussions. If you haven't registered for tomorrow's session, you still have time. You can actually go to bit.ly/go to hyphen DS-CONF22, and you'll be able to register yourself for the tomorrow's session. Well, to cut the ribbon and launch the gala event, we have none other than the CEO of GoTo Group and GoTo Financial, Andre Soelistyo. Andre has played a pivotal role in GoTo's rapid growth and long-term business sustainability. He directed the expansion of GoTo's business by securing key strategic partnerships and establishing the company's corporate functions. He joined the company in 2015 as Gojek's president, where he led over $5 billion of fundraising and successfully expanded its payments and financial services businesses. Prior to joining Gojek, Andre was the executive director for North Star Group, Indonesia's largest private equity fund. He was previously the head of corporate finance at one of Indonesia's largest coal mining contractors, PT Delta Dunia Makmur. Well, it's truly my honor to introduce him. Pak Andre, we can't wait to hear from you. The virtual stage is all yours.
Thank you, Gaurav. Hi, everyone. Morning, good afternoon, and good evening. I'm here to obviously officiate and open this amazing first of its kind conference that is actually hosted by GoTo. And this year is actually very, very interesting because we put together all three very successful products that actually been engaging with a lot of the customers in Southeast Asia, which is Gojek, Tokopedia, and GoPay or GoTo Financial, and be able to kind of share a lot of the journeys and learnings that we have in building our capabilities in data science. But I think as Gaurav mentioned, what's unique about today is that you're not going to hear it only from us or the people in our organization, but a lot of people and experts and thought leaders from the global community as well. And most importantly, we're also gonna hear a lot from all of you. And I think this is kind of the uniqueness. I do believe that the data science and the utilization of data is actually very integral in many of digital first companies in this part of the region. But I think we can do more. And this conference hopefully can be the first amongst many to come, and not only this version, but more versions to come that is hosted by many communities that's being built by this kind of engagements and whatnot, so that we can actually expand and extend a lot of the excitement of very focus on data, and also build this community to be very, very strong in this part of the region. And that's actually what going to benefit all of us. So I've been told that, the conference is going to be 3 days, and it's actually going to be in multiple formats, and inviting, as mentioned, a lot of thought leaders amongst the global community. So we can not only learn from a practical approach from this part of the region, but also a lot of success story and maybe failure stories amongst the global communities as well, so that we can actually learn, adopt, and also then experiment more in understanding what the right solution will be. I was also told that there's more than 3,500 register of participants that is actually very, very interested to actually join in one of the days. I'm also told, and then this is kind of very very important piece, that the communities that we also engage and invited, it actually includes the participation of a few communities. So for instance, She Loves Data, the AI professionals and data science Indonesia, which again, a very important collaborations to actually ensure that we can expand the engagement to larger and larger community. So welcome everyone from that organization. And hopefully over the next 3 days, we'll be able to see opportunities to kind of showcase a lot of the practical work that has been done from many of the organizations, including ours. Discuss new and exciting technologies. Of course, every day things change and things actually evolve very significantly and very fast. And learning and hearing about all that new trends is very, very important. And then hopefully with a lot of the leading experts, and then we get to hear a lot of these excitements as well. So I think my last parting comment is, have fun. And hopefully this could be a two-way conversation. Unfortunately, it's not a face-to-face conference. Otherwise, it will be filled with many great social activities as well. But I think hopefully, we all pray that this year is the beginning of an end from the pandemic, so that the next version of this can be maybe done in Bali or definitely in person, so that all of you can be here with us, and then we can build this community more socially as well. And nevertheless, again, have fun and enjoy the conference. And I hope to see you, very soon as well. Thank you. Thank you, Gaurav.
Thank you so much, Pak Andre. First of all, for taking out time from your schedule and opening the first ever GoTo Data Science Conference. And you're absolutely right. This is just the first of the series. We're going to have more in the coming years. Next, friends, I would like to introduce you to Kevin Aluwi, CEO of Gojek. Kevin is responsible for leading GoTo's on-demand business, that is Gojek. Since founding Gojek, Kevin has held significant leadership roles across product and functional teams. He has developed deep technology expertise across Gojek's data, engineering, and product teams, with a focus on enhancing the platform's overall user experience. Prior to his role at Gojek, Kevin spent a couple of years at PD Fashion e-service, which is basically Zalora Indonesia, as the head of business intelligence. And earlier in his career, he also worked as a business development manager at Merah Putih Inc., an Indonesia-based investment firm. Kevin's commitment to continuously innovate also led him to be accredited in the 2016 Forbes 30 Under 30 Asia list for consumer technology, and in the 2022, this year, Forbes Indonesia's 40 Under 40 list. So the whole GoTo family is very proud and congratulates you, Kevin. So as I invite Kevin to his remarks, I'd also request him to share how data science has helped Gojek grow and how do you see its role in future with GoTo. Please join me in welcoming Kevin. Kevin, over to you, please.
Hey,
Kevin?
Your audio is not connected.
Hey.
Perhaps it's
all right. There we go. Sorry about that. What I was saying was that I've always been really, really passionate about this space from day one, and I've been really fortunate to have been working with so many people in Gojek who share that passion and to see how data can be used to deliver better customer experiences and also better business outcomes. I think the journey to get here was fairly difficult, and I would say the rest of the team probably think that continues to be challenging. I remember the first time we set up our data science function was we decided to open a center in Singapore, and this was in, I believe, end of 2015, mid 2015, something like that, and we were the first company in Indonesia to do so. And since then, the function has grown to various different countries. At one point, we even had folks working out of the US, but today we have people working on data and data science across Indonesia, Singapore, and India. And we've really grown the function tremendously to not also, it's not just about data science, obviously. We have data engineering, business intelligence, and many other kind of supporting functions across the org. And all of those actually help us to deliver better customer experiences and better business results across Gojek. I mean, everything from probably the more obvious things like programmatic dynamic pricing for our services, to even things that might seem smaller but also really important around, for example, what chat recommendations do we give to the consumer and the driver when they're talking to each other, so they can save typing time and typing effort. We're really big believers in the ability to ingest all of these various different inputs, statistics, to actually create these superior experiences. And we really believe that the really best customer-oriented companies will always be using data extensively, not just in terms of analysis, having great people come up with really good insights about their customers and their business, but also probably more importantly, or arguably more importantly, or just as importantly, how to use machines and decision systems in order to automate in real time, to automate and ingest data in real time to deliver these experiences. And so, this is kind of what we've been focusing on over the last 1 or 2 years at Gojek. And ever since we've become part of the GoTo group last year, we've really tried to use that philosophy and use those capabilities across the various different product lines and business lines that we have today. And we're really excited because we really think that the potential is absolutely massive. The potential is absolutely massive, and we're really happy to be sharing this across the group, but also to the public. We really think that the ecosystem is still so early in this part of the world, and we have so much to learn from each other. And with that, I just, like Andre, I wanted to wish everyone a fun conference. I'll be popping in and out of the sessions. We have some really great speakers. We have some really great case studies and sessions. So please have fun, and I'm confident this is going to be a very awesome learning and sharing experience. Thanks, everyone.
Thanks so much, Pak Kevin, for the wishes and for sharing the insights as well from Gojek. I think no doubt the data that is used to make a customer's experience better is actually reflected on how customers love the experience of using the services by Gojek. Ladies and gentlemen, this marks that the GoTo Data Science Conference has officially begun. And I welcome you all once again on behalf of the GoTo family. GoTo is one of the largest technology companies in Indonesia and Southeast Asia. Our effort to organize this conference is just a small step towards sharing how our work in data science is creating a positive impact on our customers. We also want to learn from the experts in the field who we have invited as guests and discuss new and cutting-edge ideas that they are working on and we can learn from. Being a socially driven and sensitive organization, we value and cherish the involvement of data science communities across the globe towards this common goal, and you will see many communities represented in the conference as well. In this conference, we will be discussing a wide variety of areas in data science, covering NLP, causal inference, bandits, recommender systems, computer vision, search ranking, and more. This also reflects that actually there is a variety of problems that we are solving at GoTo. We are a diverse group of individuals, the data scientists, especially the data science team, So we come from a variety of backgrounds ranging from mathematics, arts, engineering, physics to business. In fact, my team also has a geography major who is an excellent data scientist. So the expertise that is required to solve problems of the complexity and the scale is ranging from NLP to computer vision, and the scale at which we are solving these problems is massive. We work as one GoTo, that's also a hashtag, while located across multiple different locations. Our teams are located in Indonesia, India, and Singapore, and we are continually expanding. This marks the beginning, and before we begin the series of talks and discussions, we will take a quick 5 minutes break as our next guest speaker gets ready for the plenary talk. I'd like to share that at the end of the plenary talk, our speaker would be taking questions from the audience. To submit your questions during the talk, you may please scan the QR code currently being shown on the screen and keep the page open in your browser so you can submit your questions there. We will see you in 5 minutes. Please enjoy the break and be back in 5 minutes, please. Hello, everyone. Those of you who have been waiting for our next plenary talk to start, it's just a quick announcement that we will be starting the talk 5 minutes earlier than scheduled. That would be 10:05 WIB, which is the Jakarta time. So stay tuned. We will be back in less than 4 minutes now. Welcome back, ladies and gentlemen. The GoTo Data Science Conference has begun, and there is no better way to start the conference than the plenary talk. We are honored to have Dr. Nicolas Chapados among us to talk on the topic Beyond Correlation Machines, Causality Tools for Better Predictions and Decisions at Scale. Dr. Nicolas Chapados is Vice President, Research at ServiceNow, Inc. He holds an engineering degree from McGill University and a PhD in computer science from University of Montreal, Canada. While still writing his thesis and jointly with his advisor, Joshua Bengio, he co-founded AppStart Technologies in 2001, a machine learning technology transfer firm to apply cutting-edge academic research ideas to areas such as insurance risk evaluation, supply chain planning, business forecasting, national defense, and hedge fund management. From this work, he also co-founded spin-off companies, Imagia, to detect and quantify cancer early with AI analysis of medical images, Element AI, which is now acquired by ServiceNow, and Chapados GoTo Capital, a quantitative asset manager. He holds the Chartered Financial Analyst designation as well. Before I invite Nicolas to give the talk, I'd like to remind you that you can submit your questions via Slido, and Nicolas would be answering them at the end of his talk. A very warm welcome to you, Nicolas. Over to you, please.
Thank you so much for this very, very kind introduction. So it's a great privilege to be kicking off the first GoTo Data Science Conference this morning with all of you. I'm sure that over the next few days, you will be learning a lot about exciting new modeling breakthroughs and other technology advances. What I want to do this morning, however, is to take a step back and take a look at our role as data scientists and re-examine a little bit some of the fundamental ways by which we analyze data. And ultimately, how we can analyze data better using tools from the field of causality in order to improve our predictions, our decisions, and especially in the context, how we do prediction and decision-making in the context of asking big what-if questions. So in other words, what I want to focus on today is how can we, as data scientists, better model, predict, and nudge human behaviors and interactions at scale when we are dealt and when we are dealing with a sea of data. Before we do that, however, I would like to give a brief survey for some of the astonishing progress that the field of machine learning has made in the past few years. And this, I hope, will give you a feeling for many of the accomplishments that most researchers in the community thought were either implausible or even impossible as of just a few years ago. One example to start with is the field of computer vision. And as of 2017, for example, computer vision had reached the point where we could do very accurate semantic segmentation and instance segmentation of complex urban scenes in almost real time for self-driving car applications. In the same year, in fact, machine learning models had made so much progress and had advanced so much that on some measures, the performance that we would get with the leading computer vision models would exceed human accuracy on some visual recognition tasks. And in fact, the progress has been so quick in those years that the well-known ImageNet competition was retired in 2017 in the form that had driven much of the progress in computer vision in the prior 2 years. So what has explained a big chunk of the recent progress in machine learning? In fact, it has come from basically applying a single kind of machine learning architecture. Essentially, deep neural networks trained end-to-end with stochastic gradient descent. Of course, there has been a lot of progress in the architectures themselves. It's not just a single big stack of fully connected layers as we would do maybe 20 years ago. For instance, we have learned that it is typically a good idea to use a convolutional neural network to process images. And until a few years ago, we would also use recurrent neural networks such as LSTMs to process text. We also have developed a design pattern for large neural networks, such as encoder-decoder architectures, like what we see on the figure. And in the encoder-decoder pattern, typically an input signal, so in this example, an image of a motorcycle racer, would be encoded by a deep neural network into a continuous internal representation. And in this example, which is an image captioning example, would be decoded word by word by a recurrent neural network to generate a caption that describes the image. It also turns out that these models are not just good at performing recognition tasks, but they are very, very good as acting as very fancy random number generators and generate realistic looking samples from extremely high dimensional probability spaces. So in the example we see on the slide, none of the faces in the illustration are the face of a real person. All of them have been sampled by a generative model of human faces. Also, more recently, and essentially since late 2017, some of the most exciting progress has come through applications and variants of an architecture known as the transformer architecture, which was introduced by some Google researchers. And it's not my purpose today to explain transformers in detail, but in the past couple of years, since 2017, one thing about them has become extremely clear, and it is that bigger is better. We see an illustration here of how that is. What we see is the progress of transformer-based language models since 2018. And the x-axis is the date at which particular models were introduced in the academic literature, and the y-axis represents the model size in terms of the number of parameters expressed on a log scale. And the figures you see there are millions of parameters. So the scale at the low end starts at models with 10 million parameters. So what we see here is that in the span of just a few years, our best language models have gone up from about 100 million parameters to about 1 trillion parameters. Okay, this is a staggering growth in just a couple of years, a growth of 4 orders of magnitude. So what does size buy us exactly? It largely buys us more performance, and it buys us more performance when this size is coupled with enough compute capacity on the one hand and enough data on the other hand. And we see an illustration of a relationship of what size buys us here. And although the slide is a bit technical, it shows results from OpenAI that exhibit power scaling laws in the behavior of some machine learning algorithms, including language models. And the net result of those scaling laws have been some incredible applications that were barely imaginable just recently. So one example of those applications is that we can now train language models that are capable of capturing long-range interactions between words in order to generate a plausible and a realistic sounding story. Okay, so here I'm going to give an example, and just for everyone, okay, this has been generated basically from a random number generator. Okay, this is not real news, but I'm going to illustrate one example about potential investments by GoTo Group in AI. And this example was generated from GPT-3 by OpenAI. So what we see is we prompted the model. So we prepared the model by giving it the sentence in the bold red characters. And then we asked the model, okay, what are likely words that can come next and that would create a great story? And essentially the model completed with the following paragraphs, where Andre, whom we heard earlier, announced plans to double down on research efforts in AI and blockchain to stay ahead of the competition, et cetera, and that Andre really believes that this is super fundamental for GoTo Group to maintain its advances, and the company plans to invest in new equipment and software. So this sounds extremely realistic, but it only comes from a purely statistical model of language. Okay, and in fact, what comes out of GPT-3 is totally random. If you run this story multiple times, you will get different things that come out every time. We can also take transformer-based models into the realm of multimodality. So here we're asking such a model to translate from a text description that's asking for an illustration of a baby chipmunk with a mustache watching TV, and asking it to generate illustrations of that. So this particular model, called the DALL-E model, performs a really good job of generalizing there, and we see it is able to generate realistic looking illustrations that frankly have never been seen in the training set before, because the training set did not contain illustrations of baby chipmunks with a mustache watching TV. However, and this is where I want to take us, the key point is that despite all the impressive successes that we have seen so far with all those applications of deep neural networks, they fundamentally remain huge correlation machines. And what I'm going to discuss in the rest of the talk is that without additional machinery, they cannot really make sense of the causal relationships that drive much of the real world. And examples of complex causality, such as those that we see on the slide with a visual common sense reasoning task, remain very difficult for models to handle. And sometimes we want to ask and predict answers to very simple questions of a basic what if type. So in healthcare, what happens if we give this particular drug to this patient now? And in the context of commerce, how will our customers react if we increase the price? And in the rest of the presentation, we will see some of the ways in which we can tackle these questions. So to answer what if questions, the first set of tools comes from the field of causal inference. And of course, questions of causality lie at the heart of the scientific enterprise. So as we study causality, we encounter, in fact, techniques and methodologies that come from a variety of scientific disciplines, including statistics, computer science, econometrics, epidemiology, climate science, etc. So my goal today is really to give you a flavor for this mode of thinking, to raise your awareness of those techniques when you face up new data modeling problems. But of course, in the time that remains, I will not go deep into the mathematical details for applying any of those techniques. So both your statistics professors as well as random people on the internet will tell you not to confuse correlation and causation unless you face dire consequences. But what does it really mean in practice? The first and the most important question is that we must be very careful when we're trying to answer what if questions from purely observational data. So in this, for the next minute or so, I'm going to build one simple example that illustrates what goes wrong if we're not careful. Okay, it's probably the simplest example that we can encounter, but situations with that broad pattern occurs over and over. So On the slide, what we want to do is to collect data about exercise habits in a population and try to predict what will be the health expenses of an individual as they exercise more or less. Okay, so what I illustrate here is first an hypothesis about the direction of causality. Okay, by drawing an arrow from the exercise variable to the health expense variable, I am making the hypothesis that exercise has a causal influence on health expenses and a direct causal influence on health expenses. And my goal really will be to estimate this influence in order to predict as I exercise more, will my expenses go down? So I collect some data, and the data might look like this scatter plot here. And I note something very weird about this data. Basically, as I exercise more, my health expenses go up. So this is very counterintuitive. It's not the direction of the relationship that I was expecting. And the reality is that in this problem, age is also important. Okay, so I draw this new graph where I make the hypothesis that age has an effect on both exercise and health expenses. And when we take this into account, the picture that emerges is much more nuanced. So same data, same points. If you squint enough, you will see the points are all exactly the same, but now they have been colored differently by the age variable. And when I look at this data, the first thing we note is that in this population, there is a peculiarity, which is that older people exercise more. For example, maybe that their doctors told them, you're getting older, you need to exercise, and people comply. So this is one first property of this data. Also, a second property of this data is that as people get older, their health expenses also get higher on average. But if I take individuals within the same age cohort, we see that exercising more makes their health expenses go down. So here, this is the causal effect that I'm interested in. So keeping age constant, changing the exercise variable has the expected effect in terms of predicting the resulting health expenses. Okay, so this is hopefully a simple enough example that shows that if we don't take the causal structure into consideration, we can come to the totally wrong conclusion about our data. And in this example, I actually come to a conclusion that has the wrong sign, that is not predicting the right direction of effect. Okay, so those who are familiar with the literature, you would recognize this as being the Simpson paradox, but this is just one example of what can go wrong when we confuse correlation and causation. And here, just a point of terminology, age is called a confounder in this context. So of course, we have a gold standard, the randomized controlled trials to estimate causal effects. In computer science, it's also widely known as A/B testing. And there are standard practices to estimate causal effect in many fields, ranging from the approval of new drugs to computational advertising. But we cannot always use them. Maybe they are too expensive, maybe they take too long, or maybe they are not ethical. For example, it would be wrong to force half of a population to smoke just in order to estimate the causal effect of tobacco on health. So this brings us to what's known as the ladder of causation, which was introduced by Julia Pearl, who's a well-known researcher in the field. And in this ladder, each rung corresponds to progressively harder problems having to do with answering questions of causal relationships from purely observational data. Okay, so here we assume we don't have A/B testing data, just observational data. And the first level is the level of association, which is essentially what we have always done before, observing the world and asking questions about it as a distant observer without disturbing it. So an example here would be about a survey on consumer attitudes, assuming I'm not trying to change those attitudes. The second level is that of interventions. We want to predict how the world will react if we become an actor in the world. Okay, so we're asking questions about the future consequences of intervening. Will I get better if I take this drug? Or what happens from a policy perspective if we ban sugary drinks in a state or in a province, for example? And the third level of the hierarchy is also maybe the hardest to conceptualize. And Pearl calls it the level of counterfactuals. Although as a point of terminology, you need to be careful because other researchers use the word counterfactual to mean slightly different things. But in the Pearl terminology, a counterfactual question is to ask a retrospective what if question. For example, suppose that we have a natural disaster that has happened and it has had disastrous consequences. Now, given that this disaster has happened, okay, it is a fact. We have collected data about everything surrounding the disaster happening. A counterfactual question would be to ask, okay, now suppose that safety standards and safety measures had been different in a particular jurisdiction where the disaster happened. Would the consequences have been the same, or would we have fared better had we had better safety standards? Okay, so that's what we mean by asking counterfactual questions here. Now, let's examine a bit deeper what really differentiates the first two levels. Okay, so on the right, I illustrate a very simple causal graph where we have a single treatment variable, an outcome variable, and this is the variable we're interested in predicting and controlling, as well as one confounder that has an impact on both the treatment and the outcome. Okay, at level one, what we're doing basically is probabilistic prediction by conditioning. Okay, so we're just observing, for example, conditioning on the state t = 1. Okay, so we gave the treatment to the patient, for example, and we are just filtering out the output of our generating mechanism. And we pick out the cases in our set of observations where t happens to have value 1. And we look at what goes along with that. In contrast, for level 2, the level of intervention, we want to predict the result of an active intervention. Okay, so here we express it with a new notation that we call the do notation. So we force the variable t to take treatment value 1, and we want to know what would happen if we suspend the usual causal mechanisms, and that means cutting out the link between C and T. We force T to take value 1, and then we ask, okay, what are the distributional consequences of cutting out this link? Okay, so this corresponds to making an intervention in the world. It is equivalent to so-called surgery on the causal graph. Another way to understand what's going on visually is with sets. So we suppose that we have a population that's divided into two subpopulations, one that take the treatment, one that doesn't take it. And at the level of association, all that we're doing is to compute an expectation over the respective subpopulation. So computing an expectation over blue and over red. Whereas at the level of intervention, instead of filtering, we want to reason about what would happen if we force the entire population to either take the treatment or not take it. Okay, so again, this is expressed in notation using the do notation that was introduced by Pearl. Now, more broadly, this leads us to the question, is it feasible at all? In other words, are we capable of making causal conclusions from pure observational data? And luckily, the answer for us is that sometimes, yes, it is possible. Okay, so in other words, as we see on the right, sometimes it is possible to transform observational data that is generated according to a specific causal model into a pseudo interventional data that obeys or that would behave according to a causal graph that exists only in our imagination. Okay, so when we are in a position to do this, what we are doing really is transforming a causal estimation problem into a purely statistical estimation problem. And there are several techniques for doing that. One that I mentioned is called the do calculus from Pearl. There are inverse probability weighting techniques, matching techniques, and so on. But broadly, there are two dominant schools of thought regarding causal inference from observational data. The first one is that we can try to model the causal relationships between all the variables. So this is the do calculus introduced by Pearl. And it allows us to answer pretty much any causal question that we might be interested in. But we need a causal graph to be able to do that. The alternative is to model the relationships only between the variables that are of interest to us. This is known as the potential outcomes framework. And both frameworks have strengths and weaknesses. And where they overlap, they largely agree in the answers that they give us. But which framework is best really depends on the circumstances. Now, without going deeply into a lecture on causal adjustment or do calculus, I want to give you a flavor for how it's done. So we start by assuming, again, the same simple causal graph as before. And what we want to do essentially is to predict the effect of a treatment, okay? But we have confounders that come in the way. So just as a little bit of notation here, again, we have the nodes that denote random variables, the edges denote causal relationships. And as we explained at length before, the graph that results from just conditioning on the treatment is not the same as the graph that is doing the intervention. And an intuition for why this is the case is that when we are changing t, we have two impacts on the outcome y. So first, there is a direct causal effect from t on y, but then there is an indirect effect that goes through the confounder, and that will magnify the effect of changing t. And this is basically why there is this inequality between those two relationships. There is in this case, a simple adjustment that corresponds to a regression adjustment formula that lets us convert causal estimation expressions that contain do terms in them into pure terms that contain only conditioning expressions and expectations. So the nature of do calculus essentially is to provide us with a set of rules that tell us exactly when these conversions from expressions that contain do terms can be converted into pure statistical conditioning expression that we know how to compute. Okay, now I want to shift gears a little bit and move to a practical application of tools from causal inference that should be interest to many of you in the audience. And I will do this by discussing a classical paper by Léon Bottou and his colleagues on computational advertising. So the key question we're seeking to answer in the next few minutes is, how can we replay actions that we've taken in the past in order to improve our performance in the future? And the high-level computational advertising problem that's being tackled here is to decide which ads to place in response to search queries. And we assume that the ads come from an inventory of ads. So we have n of them, and each ad has a corresponding bid associated with it. And in the context, our goal is to maximize expected revenue by picking the right ads and putting them in the right layout on the page. And of course, assuming that we have run a search engine like this for a long time in the past, we would have collected a lot of data already. And our purpose is really to ask, hey, how can we improve our placement policy from the past data in order to get a better placement policy in the future? And this is a causal question. So here, what Bottou and his colleagues did was to write a causal graph for how exogenous variables, so here the user intent and the inventory, the inventory of ads, translate into revenue. So the causal graph also has a structural equation model that lists out each of the functional relationship between the variables in this graph. And very briefly, I don't want to go too much into the details of this graph, but we have from the query and the inventory, we can determine a set of eligible ads and bids, and those are fed into a scoring model, which is the key here that we will be seeking to improve, and that determines which ads are displayed in response to a query along with prices. That feeds into a click prediction model that then can give us an expected revenue from the placement. Okay, so note that here some of the functions are known and some are unknown, and we want to have ways to deal with that. One of the additional challenges in computational advertising is that there is an intrinsic path dependency in how the data is collected. So the previous experience of a user with the system impacts their satisfaction and what would be their search intent in the next time steps. And all of these act as very complex confounders, and it makes causal predictions very complicated. Okay, so one way of dealing with that is to unroll the causal graph through time and trace out the path from all the variables of interest through all the confounders. And we see that this can become complicated very quickly. But one of the nice things about causal graphs is that they make all assumptions quite transparent. If we want to make a simplifying assumption, for example, we can express it on the graph, make it clear, and this provides a kind of forum to have constructive debate about what assumptions are realistic and which are not. So back to our problem, how would the system have performed if, when the data was collected, we had replaced a previous ad placement model M by a new model M star? And in other words, what is the counterfactual value of model M star? So a simplified analysis here is to replay the historical data under interventions, and this runs as follows. So what I'm going to show is a simplified version, because we're going to assume that all the episodes are independent across time. So I'm not going to assume, the complex unrolled causal graph that we saw previously. And again, what we're trying to do is to learn how we can improve the scoring function in order to increase revenue. Okay, so just a point of warning, this note, the slide might appear to be a little bit heavy on the math, but it's actually not really complicated if you pay attention. So it's very elegant. I hope you stay with me for what comes next. So we start by writing down the joint probability distribution for all the variables. And so from the causal graph, we can write the joint distribution as the product of all the individual factors that are given by the factorization in the causal graph. And note that there are terms in there that we cannot compute, but as you will see, it will not really matter. Okay, so now what we want to do is to make a soft intervention in this graph. In other words, I want to change a single term, such as the scoring model, and we see that this corresponds to changing one term in the factorization. So instead of having P of Q given X and A, I'm going to have a different model P star, for example. And I want to compute the expected click count under the new scoring model. We can actually do this via importance sampling as the ratio of the new probability distribution to the old one taken as an expectation. And by magic, when we do this, all the terms in the joint probability distribution cancel out, except the ratio between the new scoring function and the old scoring function. And this we can just compute by simply replaying our historical data. Okay, so again, we're making some assumptions here, but the nice thing with causal graphs is that we can be very explicit about that. And of course, the proof of the pudding is in the eating. And our question is, does this technique work? And in the author's experiments, it indeed worked quite well. So on the chart, we see results for a click prediction on the left and revenue prediction on the right. And in blue are the predictions that the model are making, okay, whereby all the historical data was collected under a unique policy represented here by the square. And in blue, we have the prediction of what would be, for example, the average click per page as we change the reserve price of the mainline position within the page. So this is one specific place within the search results. And what the author did is that later on, they ran an experiment where they reduced the mainline price, and their results, their empirical results, matched very, very closely to what was predicted from a previous policy and previous data in blue by the model. And we see the same kind of good outcomes generated on the revenue prediction. So in this instance that uses a fairly complex model with tons of data, it has been quite successful. And if the topic is of interest to you, I highly recommend going back to this paper by Léon Bottou and his colleagues, as it is both super clear, a very good tutorial on causal inference, and as you can see, presenting some great results. So what I now want to turn to is to move to the topic of causal discovery. So instead of doing causal inference that we were doing previously, we assume when doing causal inference that we have a causal graph at our disposal most of the time, but sometimes we don't always have that luxury. Maybe we don't have an expert at hand that can tell us what the right graph should be, or simply there are some problems that are just too complex for an expert to deal with. And examples of that would be gene expression networks in biology or relationships within complex climate systems. So the problem with causal discovery is that we assume that we have data, most of which is observational, and we'll relax this assumption in a couple of slides. And we're looking for an algorithm that can recover causal relationships and their nature. So is it, for example, a linear relationship or a log linear relationship, and so on. And of course, in the two variable case, this can be as simple as figuring out the direction of causality. And our purpose really is either, in simple cases to replace an expert because we don't have one close by, or help an expert figure things out in the case where we have a ton of variables and a ton of data. So there's a first class of method that tries to directly search for a causal graph that maximizes some scoring criterion. All of these methods operate according to the same template. They first propose a directed acyclic graph, a DAG structure. They will score it according to some measure, and then they repeat it and they explore the DAG space this way. So we see an example here where different DAGs are tried with different scores. And finally, we hit our target DAG that gives the highest score, and this makes us happy. The challenge with all of those methods is that the space of DAGs is massive, okay? It is super exponential in the number of variables. And so this becomes quickly an intractable problem as the number of variables increases. So this means that causal discovery is hard. It's actually hard for two reasons. As we showed previously, yes, the search space is huge, but even if we had the best algorithm, even if we had infinite and perfect data, there's a second problem, which is that we will always end up with a set of graphs that we cannot distinguish. Okay, so it is a set for which there is some residual uncertainty that we cannot remove about the direction of certain edges. And in the literature, this set is called the Markov equivalence class, or the MEC, okay? And this uncertainty on the direction of relationships actually propagates on the estimation of causal effects. And this whole area of causal discovery remains a very active area of research. So I want to show two recent results that really help us advance the field here. The first one is work that we did at ServiceNow Research in collaboration with University of Montreal and Mila. And this is a paper that actually will appear in a couple of weeks at a new conference on causal learning and reasoning called the CLEAR Conference that was co-founded by Bernard Sholkoff and Joshua Bengio. And so this work is on typing assumptions to improve identification and causal discovery, okay? So at a high level, we ask questions, what sound like reasonable sounding question. For example, we know usually that when we flip a switch, we change the status of a light bulb, okay? Can a light bulb change the state of a switch? It doesn't really make sense. Okay, so we have here some a priori knowledge that there are some directions that really don't make sense in practice. The same thing, can the temperature of a city...
Dr. Nicolas?
Yes.
Just a quick time check for 5 minutes before we end the talk and move into Q&A.
Perfect. Okay, I should be done.
Thank you.
The second one is, can the temperature of a city alter its altitude? And so from purely observational data, as we said, we can only retrieve a set of equivalent directed acyclic graphs, the MEC. But if we assign types to each of the variables in the graph that we are looking for, we obtain a different equivalence class that we call the typed Markov equivalence class. And what we do in this paper is to use this to filter out really bad candidates, okay? So using type information, I can a priori eliminate relationships that really do not make sense, okay? So the key to this method here is some very strong results, both theoretical and experimental, that show that introducing type information basically gives us an exponential speed up in many cases when trying to discover the right graph. And we see, for example, that as the number of vertices increases in a particular experiment that we did, the typed Markov equivalence class collapses down to a single element. So we have perfect identifiability in this case, whereas the untyped equivalence class remains very, very large. And notice that here the size of the equivalence class is on a log scale. Okay, so we have been able to establish very, very strong speed up when introducing this technique of type. Now, quickly moving on to a different type of causal discovery methods, we'd like to understand if we can use interventional data to improve our ability to discover causal graphs. And so let's start with the same causal graph as we had previously with a new meaning to each variable. So our confounder here will be the size of a kidney stone, for example, in a healthcare patient. T will be a medical treatment to fix the stone. And R will be whether we have recovered or not. And as a recap, if we rely only on observational data, we will make biased predictions. Okay, so one thing we can do as when we do a randomized controlled trial, for example, is a perfect intervention. So we assign some patients to T equals 0 group and other patients to the other or treatment A or the other to the treatment B group. And when we do this, okay, we have our probability equation at the bottom that is equal to the interventional equation, okay? And this setup here is known as the perfect intervention setup. There exists a different type of setup that is the imperfect intervention. The imperfect intervention that shows that what happens when only the conditionals are changed, but they are not fully randomized. Okay, so we replace an edge by a different edge. We will still get some bias, but it will be a different kind of bias. What can we do with all of this? Okay, why does this matter? So almost all causal discovery algorithms that have been proposed in the literature work only on observational data and converge to the Markov equivalence class. What the work that we did in the paper I'm going to briefly talk about is that we want to use some interventional data, so some experimental data, and this will allow us to converge to a different equivalence class that we call the interventional equivalence class. And it happens to be much, much smaller than the regular Markov equivalence class, okay? And in a nutshell, when we use experimental data, we can strongly reduce the uncertainty on the graph that we obtain. So this work was presented a bit more than a year ago at the NeurIPS 2020 conference. Again, a collaboration between colleagues from ServiceNow Research, Mila, and the University of Montreal on a method for differentiable causal discovery from interventional data. Okay, and in a nutshell, what this algorithm shows is how we can obtain an efficient search using continuous optimization that supports interventional data, that supports arbitrary conditional distributions with theoretical guarantees to convergence to the right graph. Okay. Now, since we're eating into the Q&A period, I will not go over the details of the model very deeply, but essentially, we're using neural networks to capture conditional distributions of any particular variable in a graph on its causal parents, assuming a graph adjacency matrix G that is optimized through what's known as the Gumbel softmax trick that lets us convert a discrete optimization problem into a continuous optimization problem. Okay, and as we build these continuous representation for the joint of the graph and the conditional distributions, all of this gives us partial log likelihoods that we can combine into a log likelihood term for the observational parameters and separately incorporate into a different likelihood term the interventional parameters that we have through a clever reparametrization of the neural network. So again, I cannot go into the details, but please feel free to consult the paper for the details. Essentially, does the method work? Yes, it does. We recover in our experiments, we recover the correct graph through a continuous optimization process that lets us do structure learning. So in this example, we see that the correct edges converge to probability 1 almost all the time, and the wrong edges converge to probability 0 almost all the time as we progress through the optimization. There's only one difference here. You see one red and one green, and that corresponds to the direction of an edge being flipped in a particular graph. We compared this with a number of state-of-the-art other causal discovery methods. Again, these results are quite dense. I will skip over them, but they show that the method pretty much outperforms the competition in cases where we have known target interventions as well as unknown target interventions. Okay, so very, very strong results under a wide number of experimental contexts. And so what are some of the takeaways from this talk? The first one is that if we're trying to make what-if predictions and we don't account for the causal structure of the data, our predictions may very likely be biased or can even have the wrong size, the wrong sign. And this is regardless of the amount of data that you have or the cleverness of the machine learning architecture. So even the very, very clever transformer-based, large models that we discussed at the beginning would be impacted by those kinds of problems. Fortunately, we have tools from causal inference that can help us make unbiased predictions from observational data. We also have tools from causal discovery that help us when we don't have a sense for what the right causal graph might look like. And as you have seen from work that came out recently from my team, as well as work from the broader community, both areas remain a very, very fertile ground for research advances. And of course, I would be extremely happy and thrilled to continue the conversation and discuss what are some of the causality problems that data science people at GoTo are experiencing. Again, before closing, a word of thanks to many of my friends and colleagues that helped out with this work. And on this, time to thank you and time to turn over for questions.
Well, I think it's time to thank you, Dr. Nicolas, for such an amazing sharing. That was not only insightful, I think this was most dense per minute knowledge that I have observed in a very, very long time. And that too in a such structured, the kind of examples that you gave. Thank you so much. And this is not only for me personally. We have over, 7,600 viewers right now on Tokopedia Play and our other YouTube channels as well. So a lot of these people have flooded the Slido with questions. Very overwhelming response. And I would like to thank the audience as well for your questions. Unfortunately, due to lack of time, we would not be able to address all of them. But what we will try to do is all the questions that we have gathered, we'll try to create an FAQ later and probably blast out to the registrations, right? Now, however, I will take a few questions that we have picked from our audiences. So, Dr. Nicolas, some of our audiences are actually interested in knowing your background, because how you've reached where you've reached, especially from the machine learning perspective. So, would you like to share some bits with the younger people in the audience right now? How has your journey been in machine learning?
Yeah, with great pleasure, Gaurav. So my background is I started with an engineering undergraduate degree. So I studied computer engineering at McGill University in Montreal. And right after graduation, I was very fortunate to be accepted for a position within the speech recognition research unit of a well-known Canadian telecommunication company at the time called Nortel Network. This was in the mid to late 90s. Unfortunately, this company has since gone bankrupt, but at the time they were running one of the top speech recognition labs in the world. And so this gave me a taste and a feeling for the potential of machine learning. It made me decide to go back to school and to do a master's and a PhD, joining Professor Yoshua Bengio's lab at the University of Montreal at the time. So this is how I got to know Yoshua. Of course, in those days, he was much earlier in his career, was not the celebrity that he is today. But there was, this element of drive and this spark in him that was very, very powerful for me, and that was very inspiring. So this is why I decided to join his lab. And then him and I, together with two other of his then graduate students, we started this technology transfer company in the early 2000s. And this really started, out of academic work that we were doing for a big insurance company. And we were developing methods based on neural networks that were just so fantastically better than the methods that actuarial mathematicians were using at the time, which was basically just generalized linear models for risk estimation purposes. And so we decided, hey, we're very young and naive. Let's start a company to try to, bring that to the market. Of course, it was quite hard. And it even though, ultimately our foray into insurance was not very successful commercially, we also had the opportunity to work with a number of other teams. So we worked, for example, in hedge fund planning. We worked in schedule optimization in the business world. We did some work for the US Department of Defense as well. All of that ultimately crystallized some ideas in our minds about the potential for AI in the broader field. And this resulted in creating spin-off companies, like you mentioned at the beginning, Gaurav, in 2014, Imagia, that was aimed at using AI to detect and diagnose cancer on medical scans, as well as Element AI, where I met our colleague here on the call, Sylvain Truong. And Element had a purpose of democratizing AI for the enterprise and improve the quality of decision-making in large organizations through a better use of AI techniques. So this has been, quite a journey. I always had the privilege to, keep one foot in academia and one foot in the business world. I appreciate that not everybody has the privilege that I had, but for me, it was a very, very nice way to help facilitate this transfer of ideas and make new cutting edge ideas from research available more broadly in different areas of industry where they can have real impact.
Fantastic. Thank you so much for sharing, Nicolas. And I think you're talking about your journey starting in 2000s when data science or machine learning was not as widespread or commonplace as it is today. So I think for our younger audiences in today's time, sky is the limit. And thank you for setting such good examples, Nicolas. Now, I think since you have There are certain comments from the YouTube live which basically says you've compressed 100 hours of lectures into 40 minutes. So we do have questions, of course, right? So one of the questions from GoTo perspective, our data basically is constantly biased by human decisions, which is true for many companies, right? Let's say from marketing decisions, marketing teams basically run campaigns, or even from machine learning models in production, right? So we've been using causal inference to predict treatment effect, but we've basically not moved into or touched causal discovery. So how are these fields related, and how do they complement each other?
Yeah. So as you mentioned, the two fields are quite complementary. And if causal inference for you today is giving good results and is making accurate predictions, then maybe you don't even need causal discovery. Really, the premise for causal discovery is to help you get to causal inference when you don't even have an idea of what a causal graph looks like. Okay, so you have a pile of data. You don't know what the causal graph looks like, maybe because you have too many variables, or just because, you know, from an expert perspective, the relationship between those variables are too complicated. Okay, and this often happens in computational biology, for example, where you have gene regulatory pathways that you really have no idea which can cause what. Okay. The same in climate modeling, for example, where the direction of causality is really not clear ahead of time. So in those cases, causal discovery is where you would want to go. It's still a very active field of research. So for example, one area where new results came out recently is how can we aggregate variables where we have many of them. Let's say in a climate system, we may measure temperature at small patches of the ocean, but we have millions of such patches. And then we want to, you know, create hierarchical aggregation of those patches so that we can express for human consumption causal relationships between much higher level variables, right? But our raw data is at a very fine-grained level. So how can we have those hierarchical relationships? So this is still very new. There are many new, many methods that are being proposed in this context. And even in our team, the work on causal discovery here is on making it more flexible. Okay, suppose you don't have observational data only, but you have some interventions as well. Well, are you able to make use of this information to get a better graph? But ultimately, you do all of this, you go to all this trouble if you don't have the graph. If you do have, a pretty good graph, or at least something you can write down and challenge, between your experts in the field, then maybe just doing, traditional causal inference for you is plenty, and will give you maybe, a big chunk of the benefits for the current amount of work that you're currently doing. So there might not be a ton of additional benefit in doing causal discovery then.
Thank you, Nicolas. Another question I would like to take from what our audiences have shared is, can you talk a little bit about the evolution of deep learning for causal inference? And do you see it overtaking legacy ML methods for causal inference? And they've also given an example of double machine learning. So deep learning and causal inference, how are they interplaying?
Yeah, so that's a great question. And actually, if I had a bit more time today, I would have given some very exciting results that my team is working on, on precisely this question. And what we're seeing is some deep learning algorithms that are able to capture some unobserved confounders, for example. Okay, so we always make the assumption that the confounders are observed. But what happens if they are not? Okay, so there is some progress, especially from David Bly's group at Columbia, for example, that came up with this, and now we're building on this work in my team as well, to develop different types of machine learning algorithms, including things like variational autoencoders that can represent unobserved confounders as latent variables, and then do causal analysis through, considering that your confounders are these latent variables. Okay, so this is quite new. This is, a bit on the cutting edge. We're still figuring out, when it works and when it does not. But the particular use case that we're considering in my team is what happens when we do this in a time series context. Okay, so what we call either in healthcare dynamic treatment regimes, where the treatments that a patient undergoes will change with time, and we're trying to predict the causal effects of a sequence of treatments. Or in computational advertising, it is just a generalization of the paper I presented from Léon Bottou, where we have a sequence of interactions with the same user. The user feeling towards the system evolves, and we want to take that somehow into account as a confounder to condition our placement policies. So there is a lot of activity in the space. We are co-organizing a workshop in a couple of weeks with some of the leading researchers in the field, all coming together to brainstorm on the topic. So yeah, I would say to everyone that listens to us on YouTube, if this is of interest to us, to you, stay tuned. A new paper on what you just described, Gaurav, is coming out from our team very shortly.
I honestly can't wait for that paper. The paper you mentioned about published by Bottou, I think that's already on the list to read. And the work that your team currently is doing is groundbreaking, absolutely. So looking forward to that paper and the workshop you mentioned as well. So, but for the beginners in, let's say, in causal inference, how do you, what are your tips? Like, how do you pick and identify the right confounder variables?
Yeah, that's a great question. And frankly, it's one thing that's very much on my radar at ServiceNow and on my team's radar, in the sense that, yeah, we're a research team that's interested in some of the cutting edge topics. But as you point out, the bread and butter of causal inference is really trying to figure out, okay, hey, what are the confounders? How do I correct for them? And, doing the regular stuff. And to me, what's really lacking is a little bit of a curriculum to introduce data scientists to the basic concepts about causal inference. How we do the basic adjustments, how we, the contrast between when is a potential outcome solution better and when is a do calculus type solution better, and those things. So we're working on some internal basic training at ServiceNow to teach the broader data science population about these things for our internal use. But I totally agree with you that this would totally benefit from a more widespread distribution and a more widespread exposure. But for people that are interested in getting into the field, I cannot recommend enough the paper by Bottou that I discussed. This is probably one of the most clear introduction to the field that exists. And for people that are interested in book length treatment, a very nice free resource that people can find on the internet is a book entitled Causal Inference: What If by Miguel Hernan and James Robbins. And we will have a link to that later in the notes.
Thank you so much. I think the Q&A session is turning out to be even better, yeah, even more dense. So Causal Inference What If is the book that you recommended, and completely agree. I think there is a significant lack of structured learning path around causal inference, causal discovery that is a gap in the community that can be filled. So absolutely agree. Thank you so much, Nicolas. I think we have actually already crossed the time for Q&A round as well. So I would finally, on behalf of our GoTo family, and all the audiences who have been really enjoyed listening to you. Thank you, Dr. Nicolas, for the time that you've taken out. It has been an honor to have you with us. And we continue to look forward to learn from you as well in the future.
It has been a great pleasure. Thanks for inviting me, Gaurav. I hope everyone listening to us right now has a great time at the GoTo Data Science Conference. And of course, I would be thrilled to continue interacting with the team and the conversation around causal inference.
Thank you so very much. To all our Nakama and Go troops, stay tuned for the second half, which will be an internal session for all our colleagues starting at 12:45 p.m. Jakarta time. You already have received an email with the link to join. So there's a quick break until that time. Please enjoy that break. For everyone else who is listening to us through YouTube Live and to various other channels, Tokopedia Play, thank you so much for joining us on the first day of GoTo Data Science Conference. Tomorrow, we have an equally exciting lineup of external experts as well as GoTo data scientists. And we'll be waiting to see you tomorrow at 1:30 p.m. Jakarta time. Until then, ciao. And please stay safe and take care.